Hello everyone. Today we are going to prove Gaussian law. So Gauss law of flux states that in a closed figure, the net flux can be given by the expression Q net upon epsilon naught. Today we are going to look at a very logical proof of it instead of focusing on the rote learning that we are taught in our coaching or schools and so on. Let's get started without any further ado. So, the proof that I'm going to present to you today is going to be a three-step proof. So, the first step is to figure out the flux through a sphere in which there is a plus q charge placed at its center. So, we need to figure out the flux through this sphere. Consider it a sphere, ignore my bad drawings. So, how do we proceed? Okay, so first of all, we know that the net flux is given by the expression E ds. Okay, this is how we get the net flux, right? Then we can write it as E ds cos theta. Now, I need you to analytically look at something. The electric field will be radially outward for all of these small points, these small elements that we are considering, right? And at all these small elements, the surface area, the area vector is also going to be perpendicular to the surface. So what's going to happen is they are coincident, they are parallel, right? So cos theta becomes 1. Then all you're left with is E ds. Now the expression of E that we have or that we are working with is kq by r squared, right? Now, I want you to look at this figure and tell me, does the r square or the q or anything, does it vary because of ds? Like, does it vary with respect to ds? No, the answer is no, because all these points are at a distance r. So the the electric field is going to be constant for all these points, and the cos theta is also 1. So everything is going to work out very, very well for us. So we can just take out the constants and we can write it. We can write the expression as something like this. Now, you tell me, what is the integral of ds? The integral of any element is the entirety of that element if there is nothing else given to which we have to pay respects to. So in this scenario, it is a sphere. So the total area of a sphere can be given by the expression 4 pi r squared, right? Now we have in the denominator r squared, and we can write k as 4 pi epsilon naught, and here is q. So we just cancel this, and this. Now all we are left with is q by epsilon naught, right? This is all we are left with. Now the first step, we have already completed the first step, which was to prove it for a central charge. Now we have to prove the same thing all over again for an off-centered charge. So the charge is placed not at a center, right? It is not at the center now. Now how do we prove this one now? So first of all, I would like you to just pause the video and think for a bit. If you can't, then let me tell you the approach. So you can imagine a smaller sphere inside this, right? You can imagine a smaller sphere inside this, at whose center this charge is located, right? Now, what you're going to do is you're going to think of solid cones. These solid cones are known as solid angles. So in 3D space, the angles work in solid geometry. Like in solid geometry, 3D geometry, the angles are given by these small cones, right? These small cones are what gives us the angles in 3D geometry. So what we basically get from it is that both of these spheres are made up of these cones, right? So the angle is going to be same for them, right? And these elements are cones, right? Basically, we can consider these conical elements, right? Now what we are going to do now is we are going to equate this portion's flux with this portion's flux. So if we can equate the flux through this element and the flux through this element, then we can equate it for all the angles, all the solid angles. And if we can equate it for all the solid angles, then the flux will be equal to q by epsilon naught, because we have already proven the flux through this sphere to be equal to that. So we are already halfway there. We just need to equate both of these. Now, how do we do that? How do we do that? So I want you to look at it in a 2D way. So basically a cone is like this, right? But we are going to look at it sideways. So it looks like a right triangle to us, right? It looks like a triangle to us. So what we have with us here is, let's just call this r, let's call it r prime, let's call it this radius, the radius of this circle, as L, and let's call it L prime. Okay, so we have with us L, and we have with us L prime, and we have R, and we have R prime, right? Now, first of all, I would want you to think of a way to prove it congruent. So how do we prove these two triangles congruent? Well, it's very easy. It's actually very, very easy. So the way we can do that is, we can either consider it a right angle triangle, because it is a cone, right cone. So we can prove this congruent to this and this congruent to this, and by that we would get that L upon 2 upon R equals to L prime upon 2 upon R prime, and we can just cancel out the 2's, and we get L upon R equals to L prime upon R prime. So we have gotten the ratios of these quantities. Now what I want you to do is figure out the electric field at this point. The electric field at this element can be given by the expression kq by r squared, and the area at this element, the area of this element by itself, can be given by the expression pi L squared. And now we have to equate it with this element, right? The flux at this element. So the electric field is given by kq by r squared. Then we can give the area by L prime squared, right? R prime squared and L prime squared. So this is what we have here. So we already know that these are equal. So this is going to be equal to this, and these are already equal, right? So what we get from it is that the flux is going to be same for all these solid cones, and if it is same for all these solid cones, then it is basically going to be the same for the both spheres. So we have completed this second step of this 3-step journey, right? We have completed the first 2 steps. Now the third step is a little bit complex. It would require some more analytical abilities. So what I'm going to do is I'm going to draw this complex figure, right? Oh my god. Okay, so I'm going to draw this complex figure, right? Now I'm going to place a charge plus q inside it, arbitrary position. There is no pattern to this position, right? It could be anywhere. It is just a general point. Now I want you to do the same thing. I want you to imagine a sphere at whose center this charge is located at. Now I want you to again conceptualize it with the help of solid angles, right? These solid angles, I want you to conceptualize them with respect to that. Now, the proof is essentially the same, but where you might get stuck is that these are not perfect cones anymore, because the surface here is arbitrary. So what happens is it is a shape like this, somewhat like this. Okay, so it's a shape like this now. But what we need to remember though is the fact that when electric field lines are coming at you, right, and they're coming like this, then it does not matter if they are flowing through this or if they are flowing through this, right? Because we also consider cos theta, the angle between them, right? So essentially what happens is, even though the shape might be like this or it might be like this, we only consider this part. We only consider the circular element again, uh, by simplifying it, and we do the same proof all over again for any complex figure. And by this, we have successfully derived Gauss law, which gives us this expression for the net flux. Well, this is it for today. If you have any doubts, just post them below or mail me. I've shared my email ID in the comment section as well. Thank you very much for joining in, and make sure you subscribe and like the video. Thank you.